So what I'm going to do today is continue talking about some probability issues in matching. And last time, remember what we did was talked about longest common substring and what we could expect for a longest common substring if we have two strings of length n. And I've written the notes of that on they're up on the web with the corrections from that came up last time. Now I want to do something that's sort of related. We're going to get to a similar conclusion, but through different techniques and a slightly different problem. So in this problem, what we have is a long string, length n, and we can imagine that this is the length of a database. So n is really big. Database size, so n is very, very large. And then we have a small string, s, of length m. So s is some query string. So typically in a database search, you're going to ask, is m somewhere in this longer string? Is it somewhere in the database? And I mean, I'm really thinking of the database as being all of the sequences in the database being concatenated. So you do have the possibility that you have some synthetic matches where s matches to some end portion, some suffix of one string, and then the next string that it's concatenated to in the database, it matches the prefix. But ignoring those little problems, we're going to ask whether s matches into this long string somewhere. And the question that we want to address today is, what should we expect if these two strings are random? Okay, so question. So here's my database D. If D and S are random, exactly the same generation that we had last time, we're going to pick each character with probability 1 over z. Probability P defined as 1 over z. Uniformly at random. So if D and S are such strings, then what's the probability that S is found somewhere in there? And when does that probability get small? When is it large? Because, again, let me remind you why we care about such questions. If this is a real biological database and this is a real query string, and you find a match in there where this is, let's say, inside some other longer sequence, some protein sequence or DNA sequence, when do you get to say, I think that matched because S really is related in some biological way to some longer piece that it matched into? Or when do you have to say, I can't conclude that yet because even if this was just junk, even if this is just random, there would have been a good probability, a high probability that this would have matched somewhere anyway. Okay? So these are critical questions. When we look at BLAST, that's a very central part of BLAST that does those computations for you. BLAST is much more complex. The statistics are much more complex because they haven't assumed this kind of random distribution, but a distribution that's based on the actual frequencies of the characters. But let's see if we can analyze this and relate it to the question we asked last time. So last time we looked at longest common substring. Given what we saw there, does anybody have any intuition about what we can learn from this question? Well, actually, I never finished the question. If D and S are random, when well, when is there a large probability that S will be found in D? And what does it depend on? All we have here really are P, or equivalently that's Z, M, and N. Okay? So P, N, and M. The answer has to be somehow in terms of P, N, and M. All right. Given what we did last time, where we found that where we analyzed longest common substring, this is no longer longest common substring. You're interested in whether this whole thing matches there somewhere. Does anybody have any intuition about this? Or anybody able to guess what kind of result we're going to get? Okay, well then let's do it. So we want to answer this kind of a question. All right. So the analysis actually starts out similar to what we did last time. For any starting point, let's say position I in D, the probability that S matches entirely is what? So we just have some particular starting position I, and I want to know whether S is found there. And D is some random string. Each character is there with probability P. So what's the probability that S matches all the way from here to here in D? This is not that different. In fact, it's identical to what we did last time. It's P to the M. Thank you. All right. Okay. So the probability that it does not match there, of not fully matching, is 1 minus P to the M. Okay. All right, but now I want to know what's the probability that it doesn't match anywhere. Okay, actually, ultimately, I'm interested in what's the probability that matches at least once somewhere. But the way you usually get at those kind of questions, the somewhere type questions or the at least once type questions, is you answer what's the probability that it doesn't match anywhere, ever, 0, and then you subtract that from 1. So now this is actually a subtle question. Here we have the probability that it doesn't match at a particular position I. All right. And we have roughly n. I'm going to assume that n is huge, huge, huge compared to m. So we have roughly n starting positions where S might match from. Okay. And if the question of whether it matched completely at one position was independent of the question, or the probability that it matches completely at one position is independent of the probability that it matches another position, then the answer would be 1 minus P to the M raised to the N. Okay? So let me just say this again. If the probability of fully matching at position, or starting at position I, is independent of the probability of matching at another position J, then the probability of no matching, no full matching, at any starting position is, well, 1 minus p to the m. That's the probability of not matching, not fully matching at any given starting position. And there are roughly n starting positions. So if these probabilities are truly independent, I could just do that, right? So if the probability of matching at position, starting from position 1, was really independent of the probability of matching fully at starting at position 2, and so on, then this is, except for the fact that n is, this really should be like n minus m, but n is huge, so I'm not going to worry about it. We can just multiply those different probabilities together, but you're only permitted to multiply probabilities together when the events are actually independent. So here's sort of the hand-waving heuristic part. When most people do this analysis, they just say, well, let's just assume they're independent and kind of get some answer that's not too far wrong. And if you study it more deeply, even with dependence, it doesn't hurt you that badly. I don't really like that. Another way of doing this, however, is to look at your long string and break it up into non-overlapping pieces of length m. Okay? And then you have break it up into non-overlapping pieces of length m. And then the probability that S matches here is independent of the probability that matches here, because there's no overlap between the two strings. Okay, so since we picked every character randomly, whatever happens here can't have any effect on whatever happens here. But then we don't have n starting positions anymore. We only have n divided by m. So if I work out on that basis, what's the probability that there's at least one match? Is that going to be too big or too small compared to the true probability? Too small, because you have fewer possible places that you're considering S to match in. Okay, so that's another way you can try to do this. And when you get an answer, which of the kind we get, you'll learn that when n is of a certain length, a sufficient length, the probability of matching is high. And since that estimate is, in fact, too low, then the probability of real matching is even higher than that. And the moral will be still the right moral, that when n gets past a certain length, the probability of a match, even at random, is very high. So you have to be careful about over-interpreting the meaning of a match. Okay, we could do that. But instead, I'm just going to take the easy way out, sort of to say, assume so, even though we know it's not true. And we'll still get the form of the solution, and you'll build up some intuition. This is common when you deal with probabilities where things are complex. You first say, well, let's assume something's independent you actually know is not, and see what you can learn from that assumption. And oftentimes that gets your intuition going, and oftentimes it's not far wrong from what happens when it really is, when you do the full analysis with dependency. Okay. So we'll take this as the probability that no full matching at any start. And another way of asking, I guess, the same thing is, do we think this is too high or too low compared to the right answer? See, there's some possibility of dependency. Okay. If S matches here, I don't know what it is, but if S also matches one place to the right, how can that possibly happen? Okay. It means that this character has to match S. Let's say it's an A. That's the first character in S. Let's say that's an A. And then this next character, which happens to be the first one in this positioning of S, has to match the first character also. Okay, which means that these are both A's. Okay, and then the second one, if this matches, so we now learn that this has to be an A. And then if the second one here matches, if this matches, if this matches this, and this, of course, matches that by definition, and this matches that, then again we've learned that all three of these things are A's. What I'm getting to is the following thing. If S matches at starting at some position, let's say 50, and it also matches at some position, say, starting at 51, the only way they can happen is if S is all of one, is the same character all the way through. You can think about that at home. So S has to be this sort of unusual thing, or maybe it's all T's or all C's or all G's. Okay? So when I made the assumption, the independence assumption, that the probability that S matches starting from here is the same as the probability that S matches starting from there, am I being too optimistic or too pessimistic? Well, I'll let you think about that one. We're assuming this thing, and we'll get an answer based on this assumption, and then on the midterm, I'll ask you whether that's too big or too small. Just kidding. Seeing who's awake. All right. So, what does this thing look like? Did anybody make any headway on turning this into something that looks useful? It goes to 0 as? Well, you're saying if P and M are fixed. Okay. Well, here's what I want to do with it. I want 1 minus n, P to the M over n, raised to the n. Okay, that's certainly okay, because I can just cancel the n's and nothing has changed. All right, now what does this look like to anybody? It's what? Okay, so hopefully you remember from calculus, and I'll remind you in a minute. Well, here, 1 plus 1 over n to the n converges to e, right? As n goes to infinity. E, which is what? About 2.7 something or other. I don't know. And if I have a k up here or something else, then that's e to the k. Right? So what do we have here? Up here we have np. We have minus npm is our k. So this thing should converge to e to the minus n p to the m. Kind of ugly. The minus means this. npm. Okay? So now remember, this is the probability that you don't match anywhere on the assumption of independence. And P generally is going to be fixed. That's like I mean, for any problem domain, we know what p is. That's not a variable. It's a fourth or a 20th, something. Okay? And n is also going to be, m is going to be relatively small. We're asking queries. Even small can even be 100. Okay? If we're talking about a protein, but we're looking in a database that has billions of characters, or it could really be small, something like 10. But it's reasonable at least to look at this at the moment to say this looks like about 1 over e to the n for, well, to some power, but anyway, for p and m fixed. So I just put it this way because what happens to this when n grows? Bigger or smaller? Okay, as n grows, e to the n grows, and 1 over e to the n decreases. And the point is very rapidly, because the n is in the exponent. Okay, 1 over e to the n falls rapidly as n increases. So remember what this is. This is the probability that we have no match anywhere of S. S does not fully match anywhere in the database. And we're just getting, in a sense, at this point, the obvious conclusion that, well, no, as n gets bigger and bigger, the probability that it matches somewhere increases. But the point is, one of the first take-home lesson is that it increases very rapidly. And again, this is the probability it doesn't match anywhere, so the probability it matches somewhere is 1 minus that. And since this whole thing is falling very rapidly, 1 minus that is growing rapidly. Okay, that's sort of, in a sense, what I want you to remember 10 years from now. But what I want you to remember a few months from now is more precise. Okay, so we're going to go back to this full statement and look a little more carefully at that. Okay, so probability S fully matches somewhere in D is about 1 minus 1 over E npx. Okay? All right. Now, I just want to make some little estimations here. When is this a reasonably high probability in terms of NP? What happened to X? Sorry. M. When is this a reasonably high probability in terms of NP and M? So it's actually convenient to say when is this probability at least 0.63, for example. Okay. So here's a question. When is this probability around 0.63? That's, a reasonably high probability. Okay. Actually, ultimately, we'd like to have it to be close to 1, but this is a convenient one to look at. Or in other words, E, 1 over E to the NPM should be about 0.37. Okay, well, actually, I picked, this wasn't just an arbitrary choice. Anybody recognize this one, or this one, maybe? 0.37. Yeah. It's what? When which everything is 1? When NPM gets to be 1, in other words, 0.37 is, it's 1 over E, yeah. Okay, so this is equal to 1 over E. Okay, so 1 over E is about 0.37. All right, so you get a reasonably high probability that you'll find at least one match when NPM equals 1. All right. So this is probability of full match somewhere in D is about 0.63 when NPM equals 1. All right. Now, another way of saying that is N is equal to 1 over PM. So, I don't know, my little n's all of a sudden became capital N's, but it doesn't matter. This is the database size. Is the reciprocal of the full match probability at a given site, a given start. So the probability that you had a full match starting at a given position was p to the m. And the reciprocal of that, when n is the reciprocal of that, then the probability is reasonably high that you're going to have a full match somewhere. And that's an easy shorthand to remember. Comes up a number of places. Well, let's actually express this somewhat differently in a way that, well, actually, let me do a little numerical example first. Okay. So let's say P 1 over 20. That's for protein. That's for amino acids, assuming they're uniformly distributed, although that every amino acid is equally likely in the database, even though it's not true. Okay. Okay. Actually, no. The full example I want to do here is back to DNA. 1/4. And let's take x equals 10. Okay, actually, using this thing, m is 10. So what size database, therefore, would not surprise you if you were to find a complete match somewhere of a query sequence S that was of length 10, okay, with the match probability as a quarter. So according to this thing, n equals 1 over 1/4 to the 10th. Okay. So what's 4 to the 10? Anybody know what that is?
A million.
It's about 1 million. Yeah. 4 to the 10th, about the same as 2 to the 20th. 2 to the 20th is about 2 to the 10th times 2 to the 10th. 2 to the 10th is about 1,000. That's 1,024. 1,000 times 1,000 is 1 million. So this is about 1 over 1 10 to the 6th, so that's equal to 10 to the 6th. Okay, so the bottom line here, the moral is, if you have a database that has even as little as 1 million characters, that's a small number, and you have a random sequence that's of length 10, it's not that surprising, it shouldn't be that surprising if you find a full match of that small sequence of length 10 somewhere in that database of size 1 million. So if you find that match, you don't get to go out and claim your Nobel Prize for finding some unusual matches. And I can assure you that people have made these kinds of mistakes repeatedly, and they've gotten them published. I'll show you an example later where you'll have a sequence that's relatively short and a database that's pretty big, and you do a query looking for where that short sequence is in the database, and you find that it's inside some protein or some DNA sequence that you wouldn't have imagined, or you wouldn't have imagined previously that there would be that match. So you end up finding, something taken from smallpox, a sequence from smallpox, showing up matching in a mouse sequence, or some association that you hadn't thought meant anything, or you would have expected previously, and then you build a big case around it, saying you found some amazing connection between these two organisms that nobody had previously suspected. But the kind of calculations that are done here would show you that that wasn't that surprising. All right, let's put this in a different form. N equals 1 over p to the m. N equals 1 over p, npm equals 1. Well, I'll start it this way. There I have it. How do I turn this into something that looks more familiar? Or let me turn the question around. How do we relate, if we wanted to say, there's a reasonably high probability that S will fully match when M has a certain relation to N. I need to solve for M, right? So I'm going to do what I did last time, although this time I should be on a safer ground because this is an equality. Okay, so I'm going to take the log base p of both sides, and I'm not going to have to worry anymore whether log is increasing or decreasing for this base of p, okay, because I have an equality. All right, so this is log base p1 minus log base p to the m. So log base pn equals 0 minus log base p to the m is just m. Okay. So log base pn equals minus m, or equivalently minus log base pn equals m, and that's equivalently, put it right over here, that is equivalently log base 1 over p n equals m. And 1 over p, remember, was z. So log base z n equals m. And that's what we were shooting for. So the conclusion is that when m, the length of the sequence, the query sequence, is about log z to n, log base z of the size of the database, then you have a reasonably high probability. Here we said 0.63. You have a reasonably high probability that you will find all of S. S will match completely somewhere in the database. Okay? So when M is about log Zn, it is not surprising that S matches fully. Somewhere in D. And what happens when M is even smaller than this? Should you be more confident or less confident that S will fully match somewhere? More confident. Yeah, the probability of a full match increases as S gets smaller. We already said it decreases as S gets bigger, as M gets bigger. Okay, so this was supposed to be sort of pulling a rabbit out of a hat in the end, because we came back to essentially the same conclusion that we had last time. Last time we were looking at two long sequences of equal length, and we were asking what was the we were examining the question of the expected length of the longest common substring. And what we learned was that when we get a length about twice this, then the expected number of times we're going to see that, a match somewhere in there, was still bigger than 1, about 1. Okay, so one could just generally expect, I'm being very sloppy about the word expect. Expectation and probability is not what you expect, but I'm using it that way. So last time we showed that the expected number of matches of length twice this, when we examined the longest common substring question, was close to 1. So we had a high expectation, a good chance of actually seeing one in there. But as the length of R, we called it R, as the length of M got bigger than R, that probability dropped very rapidly. The expected number of matches you would see was less than 1 and fell very quickly. So here we're coming to the same kind of moral, even though the actual setup of the question is different. Now we have just one short string and one long string as opposed to two long strings. And it is kind of fascinating that when we have two long strings and we have all those different places you could start from, as opposed to this setup where you have one long string and one short string, that the starting places are only equal to n squared pairs of them, that the answer we're getting here only differs by a constant out there, a factor of 2. So, okay, so what are the take-home lessons? It's this reciprocal relationship. When the size of the database gets to be about the reciprocal of the probability of a full match at any given single start place, that even up to there you have a reasonable probability of matching. Even if M is this big, or another way of saying it, when the database gets to be this big, you have a reasonable probability. And reasonable here we're saying is 0.63. I could ask you to try to figure it out where it gets to be 0.99, say. But the other way the other take-home lesson is that when the size of the database is log to the number of characters in the alphabet, when that log is about the size of the query, then you still have a reasonable probability of finding the query fully somewhere in the database. Okay. Well, this is page 1 of about 40 pages I have of notes on similar things. But based on how slowly this is going and how enthusiastic I can see everybody is for this kind of stuff, I probably won't do a lot more of this until we get to blast statistics. And there, all I can do, is it's way too complicated to try to derive any of those, all I'm going to be able to do is to show you what those are, and then to say, well, they kind of smell similar to some of the things we derived here. You're going to see formulas that kind of remind you of this stuff, but are much more involved. Okay.